Welcome to TennaTalk, a journey of discovery about all things antenna. TennaTalk is a production of the Antenna Whisperer. That's me, Rudy Wiedemann, K7RAW, and it is dedicated to my dear old antenna, whose words will always resonate with me. This is podcast number 9 on demystifying resonant versus non-resonant antennas. So here's a little cartoon to start off with, and the caption reads, "Yes, I really am running just 5 watts QRP, although I suppose I do have an above average antenna system. Ha ha ha." So here's a cute little cartoon on resonance, where here we have a radio where the length determines the resonant frequency, as we all know. And so the length of a swing also determines the resonant frequency of that swing. What is the natural frequency of this pendulum? And the input frequency of pushes matches the swing to achieve resonance. And here we've got an adult pushing this little girl with some voltage or potential or pressure. And that creates a current or motion of the little girl on a swing back and forth. And when V and I are in phase, voltage and current are in phase, we say it's resonant. Now, the impedance, remember, is voltage over current. And what that means is the matchup between the pushers and how much he pushes and how big a load you have. So in the case where you have a girl, let's call her 50 ohms in resistance, and you have a big guy, then he might be pushing with a lot more current. And vice versa, if you have a girl pushing the guy on the swing, you've got a much bigger load, might have an R value of a couple hundred. And your transmitter that's expecting to see a 50 ohm load is going to have a hard time driving that antenna. So that's the resistive value of that. Necessary and sufficient conditions for radio communication: you need a transmitter with appropriate power, frequency, and modulation, of course. It should be impedance matched to the transmission line to the antenna, and the antenna has to be resonant, or should be as close to resonant as possible, JX of 0 ohms of the reactive part of the impedance. That means the V and I are in phase, as we know. Proper loading of the antenna of 50 ohms resistive value, that's resistance part of the impedance, the real, not the imaginary part. And accelerating electrons on a conductor away from things will get that electrical effect of radiation into the atmosphere. Let me point out that just non-resonant antennas should really be called non-matched antennas. We're going to see why here in a minute. So here's a nice little motion graphic, a little movie about what happens on a dipole antenna. And the blue arrows are the currents coming in and out of each side of the dipole. And the blue arc here is the current going above and below the axis, showing positive and negative current, sloshing back and forth. And the red indicates the voltage. And you can see the voltage peaks out at the very ends while the current peaks out in the middle. And that's why you have a high impedance at the ends, or V over I, voltage over current. Very high current, high voltage and low current at the ends gives you a high impedance at the ends, which is why you have to have a 49-to-1 on to drive an end-fed half wave, or something between 50 ohms and a couple thousand ohms if you've got an off-center fed dipole being fed over here, not at the center. So that's a good way to imagine voltage and current on a dipole starting at that point. So a few definitions. Impedance are two components: the radiation resistance and the reactive component. Reactance, a positive JX value is a net inductive system, a negative JX value is a net capacitive system. And the opposite signs will add to hopefully cancel out. Phase, remember Eli the Iceman, where E is the voltage or potential, and L is the inductor, and I is the current. And so in that case, with an inductor, voltage comes ahead of the current. And in a capacitor, current comes ahead of the voltage. Reactance makes in V and I out of phase. If you're properly, then you've got 50 ohms of radiation resistance, of real resistance. If you're resonant, the JX value is 0 and V and I are in phase. If you're matched, then you've got both 50 ohms resistance and a reactance of 0. Efficiency, here's a little calculation on antenna efficiency. Voltage SWR, return loss, high SWR, and high SWR is when the R value is other than 50, could be high or low. The ratio of which, either higher or lower, is going to be your SWR for the most part. Unless you have very high reactance, in which case it'll throw you off. And if the currents on each side of your feed point are equal, then you have a balanced antenna. A couple other core concepts are a full match is when the impedance is 50 ohms and J0 at each junction of your antenna system. You can use impedance changers. Tuners, for example, would change both the R and the JX value, but transmission line transformers like unknowns and balance only change the resistance value, not the reactance. A conjugate match, if you have a net JX positive of a net inductive system, you have to add the equivalent amount of negative JX, negative reactance, usually using some kind of capacitance in a system to get a balance of JX of 0, because they add. A tuner range from several ohms to a few hundred ohms is pretty typical for many tuners. Transmission line transformers can also help get the tuner into shooting range. Frequency. Resonance only happens at a single frequency. And a lot of people don't appreciate that. On a multiband antenna, you have to consider that. The radiation pattern. Impedance matching does not affect the radiation plot. Coax impedance. Coax impedance is affected by unmatched impedance at either end, and it can actually transform the impedance of the coax down the line. And with respect to ATU location, if the coax sees a match at both ends, then it doesn't matter which end the ATU is located at. You won't see a difference. You'll get an equal amount of loss either way. But that's not a normal situation, but it can happen. So why consider resonant antennas at all? Well, you get much more flexibility. They're often better for multiband performance. Sometimes a simple unknown can tune it to a given band if you've got mostly R value differences and the JX value is close to 0. You have more options for better directionality. There's a lot more flexibility with it. Here's an interesting thing, long wire lengths. Here's a list of the sweet spot lengths in feet of a long wire, a random length in other words, that is not some odd integer multiple of a quarter wavelength of any band. So they're kind of really special numbers, and you might want to take a note of these numbers if you ever deal with random length or long wire antennas. And most versatile are non-matched off-center feds and end-fed half waves. As you'll see shortly, non-resonant antennas are really just incomplete resonators. So let's take a look at those two components. You've got two columns, non-resonant and resonant. You've got two rows, resistively loaded and resistively misloaded. Well, in a simple case, you could be 50 ohms, but with a reactance that's not 0. A simple tuner will handle that. If you've got something other than 50 ohms, but you've got resonance of JX of close to 0, you probably could use a transmission line tuner like an unknown only and get pretty close and be operating pretty well. A lot of people do that with end-fed half waves. If you've got a non-50 resistance and a reactance of non-0, then you need a better tuner. But the happiest situation is when you're both resonant and resistively loaded properly, 50 ohms and 0 reactance, and you've got a good match. And that's what we'd like to achieve at every interface on the antenna system. A couple notes on loading. It's mostly commonly referred to as inductive or capacitive loading, but in reality, the inductive or capacitive values will will generally affect the reactance more than the actual resistance value. But in a tuner, it actually affects both. Adjusting radiation resistance can be a loading too, as we just saw. Resistive loading simply adjusts your x-axis position on the Smith chart, but reactive loading adjusts your position above or below the Smith chart. Net inductive is a positive JX value, net capacitive is a negative JX value, and you can read this out on a nano VNA. So now you know how to look at the Smith chart on a nano VNA and understand better what you're looking at. And speaking of Smith chart, here we go. If you look at the equator here, that's pure resistance. In the middle is 50 ohms. And this is the circle of SWR of 1.5, for example. Here's my 50 ohm sweet spot. No reactance. It's neither above or below the equator. If I'm over here at 9 o'clock, I've got a very low resistance value. If I'm over here at 3 o'clock, I've got a high resistance value heading towards an open. And it's a logarithmic scale, 5, 10, 20, 50, and then 50, 100, 200, 500, 1,000, etc. In the horizontal direction here. Above the equator, you've got inductive land. Below the equator, you've got capacitive reactance land. And all we've got are these circles. You can see the 50 ohm circle right here. That's all 50 ohms, as you'll see in a second. Here's some examples of the combination of resistances and reactances as mapped on a Smith chart. So let's start with the equator, okay? So below 50 ohms, if you're down here at a 5 ohms with a 0 reactance, all of these have 0 reactance. All the dark blue have 0 reactance. This one happens to sit on the 10 SWR circle, as it indicated right here. So 50 divided by 5 is 10, so that's why it's on the 10 SWR circle. If it was 10 J0, then it would be an SWR of 5, 20 J0, SWR of 2.5, 100 J0, SWR of 2, 4, and 10, respectively. So that's how you can look at that. But now let's take a look at something that is properly loaded at 50 ohms, but it's not resonant. It's off the equator, but it is on this 50 ohm circle that's coming from the 3 o'clock position, 50 ohm of resistive loading, all the way back around. If it sits on the circle, then it's 50 ohms. As you can see, 50, 100, 50, 200, and all the way around to this little X value here of 50 and 500 J value. So in that case, a pure tuner would generally do a pretty good job at that. But now, in the case of a light blue, where you have misloaded non-resonant antennas, R is not 50 and JX is not anywhere close to 0. You can see these light blue points as being the most challenging ones for operating with a tuner. And just like the one here at 12 o'clock, 10 J50, 10 minus J50 is the capacitive equivalent of that, all sitting on the same SWR of 10 circle. So briefly, let's look at different types of matched versus unmatched antennas. So I'm just not going to read this for you. You can read it yourself, but you can see that these are examples of typical matched and unmatched antennas. And of course, you've got the plastic slinky dipole, which is clearly not a matched antenna. Types of transmatch converters, or what I call TMCs. Well, tuners are obvious, manual or auto tuners. Transmission line transformers, or balance and non-ons, for example, are another way to get a transmatch, but limited. LC networks, which are used in tuners. Stubs and even special matches that you see here are often used. And I'll leave that to you to look up in the ARRL antenna handbook as to how those work. But there's a lot of different ways to get a transmatch, impedance matchup across an interface. And here's a good example of an ATU100, a little tiny inexpensive battery powered tuner that this is what's inside. You've got a bank of relays that switch in and out different values of inductance into the network, and a bank of relays that switch in and out a bank of capacitors that you can see surface mounted here, in and out, until a microprocessor decides which combination is the sweet spot for your particular situation, and hopefully gives you a good result and displays it on the little screen here. So here's a way to look at how to recognize matched versus non-matched antennas. On the left, you'll see a off-center fed dipole sloper fed at 15% from the lower end for 40 meters. And you can see nice notches. While it's not perfect, a small tuner could easily deal with this and tune the rest of it out. And these are all sitting at the bands, at the appropriate bands of 40, 20, 15, and 10 meters. In comparison, if you look at the 23-foot Comet CHA 250 HD vertical, you can see that here's the SWR of 1.5. Most of the plot from about 4 megahertz to around 60 megahertz is all below 1.5 SWR. And a lot of these notches are not in band. This is 4 megahertz, that's not a band. Then you've got 7 megahertz, that's 40 meters, close enough. But here between 10 and 20, there's no 20 meters, not 12 or 17. Well, you've got one maybe up here, a small notch. Anyway, my point being that this is characteristic of a non-matched antenna, and you definitely would do well to use a remote antenna tuner in this case, as we'll see here in a minute. So now, here's a way to look at standing waves and loading points and matching up impedances to an off-center fed dipole, for example, the extreme case of which is end-fed, as you'll see here in a moment. So let's imagine a 40-meter half-wave antenna from here to here, and the 40-meter standing current wave, we're measuring current now, the standing wave is this blue arc. 20 meters is the brown arc here. 1, 2 arcs. And notice in the middle where I'm feeding the antenna, current is almost zero, which means the voltage is very high. Voltage over current is very, very high, a very high impedance, which is why it's not going to work on 20 meters. But if we go to 15 meters, you see the green arcs. I have one of those 3 green arcs right here in the middle. And so that's why a 40-meter half-wave dipole fed in the middle can operate in 15 meters. And then 10 meters is the 4 purple arcs that you can see here. And what a non-center fed dipole does is it looks for a trade-off. In this case, I'm looking at the 15% from the endpoint. Trade-off of the currents and impedances that I will see on different bands at that point. You see that the 40 meters will give us a different impedance, a lower current requiring a high voltage to drive it, whereas these give her for 10 meters and 15 meters work quite nicely. And the 20 meters, still not too bad at 15%, probably 80% of a matchup compared to center fed. So that's how off-center fed impedance matching works. Here's a way to look at resonance with respect to antenna lengths. The middle arc is when you have a resonant tuned antenna at the resonant length that's exactly matching the half-wave wire length. But now, if you have a net inductive antenna, you've added a coil into the antenna, then the standing wave wants to be shorter. And that's how you can accommodate shorter antennas like mobile whips and such like that with enough inductive loading. If you've got capacitive loading like a capacitive hat, then you can accommodate a longer wire for that frequency. Remember, everything is frequency dependent. So this is a way to think about how inductive loading and capacitive loading gets you resonant for that frequency. So now that we're talking about resonant systems, that means loaded and resonant, That's a match system. If we have an antenna that is loaded properly and resonant, I've got a complete circle from the yin-yang, the matching halves of my antenna, all in one place. It's a happy situation. A well-tuned dipole is just that. Together they make a matched antenna system where J is 50, or impedance is 50J0. Now, in a matched antenna system like that, I could feed it with 100 watts, run it through 25 feet of RG8X, which is a bit of a power sponge. I might lose 9 watts of it, but pretty much all of that will come out the other end in radiated power, propagated power. And the antenna impedance matches the characteristic impedance of 50 ohms, and the power circulates inside of this like a tank circuit, in a resonant tank circuit, all right here in one spot. And this is what the SimSmith plot of that would look like. Here I've got 1 watt going into the coax. I've got 25 feet of RG8X, 99.999% of the power going into the antenna, and 91% of that power coming out the other end with 50J0 perfect load. So that's our starting point. Now what would happen if I went to 100 feet? Well, I'm going to lose just over 30% of the power at 100 feet for RG8X. Now I'm characterizing all of these Smith chart plots at 28 megahertz because the loss of coax goes up with frequency typically. And so I'm giving you the worst case situation for the HF bands. Now, if we have a shack tuner and a mismatched antenna, let's say we've got a mismatched antenna at 17J50, and that gives us about an SWR of 6. Well, guess what? I'm putting 100 watts in here, and 100 watts adds up to the 22 watts of return power after the reflection up here from the SWR of 6. 22 watts comes back, combines with the 100 watts, and presents 122 watts, some of which again gets lost and recycled and returned. I'm creating a tank circuit, a resonant tank circuit with a big old sponge in the middle of this thing, sucking power each direction. And so this is not very efficient. I get 78 watts out. Still not all that terrible, but you'll see when you go to 100 feet, it goes down pretty quick. So here's a Smith chart again. We start at 25 feet, a impedance of 17J50, and with our tuner on the rig side, we can see we're down to 78%. Now, if I go to 100 feet here, with the same load, I'm down to 45% output power. I've lost more than half my power. But if I move the tuner over to the antenna side of the coax, the antenna end, for that same 100 feet, I'm back up to almost 70% power, down to just over 30% power loss instead of over 50% power loss. So it can make a huge difference. And I'll point out that I verified this with Ward Harriman, the author of SimSmith. And yes, he does account for the iterative recirculating power inside of a resonant tank circuit, essentially, between your tuner, the coax, and the antenna. So this is not just a single pass. It takes into account multi-passes. Now, let's take a look in the case of the remote tuner and a mismatched antenna. If I got a mismatched antenna as SWR of 10, which would be an impedance of 10J50 at the antenna, from 100 watts in, okay, I'm going to be down to about 91 watts after less than 10 feet of coax, which is almost negligible. If your remote tuner is within well below 10 feet of the antenna, it's almost negligible. You can pretty much disregard it. And so 9 watts of that comes back, and you get out about 90 watts, which is not bad, as we'll see in here in a second. So again, let's start off with 25 feet of RG8X. 10J50 is our SWR of 10 load. We have our antenna tuner on the antenna side, on the antenna end of the coax, and I'm down to 90% power, losing 10% of my power. If I go to 100 feet, then I'm down to 68, 69% of my power. And as you can see, I'm up here on the SWR 10 circle. If now I move the tuner to the rig end with 100 feet of coax with the same load, I'm down to 33.5% power. I lost 66. I lost 2/3 of my power this way. So you can see how sensitive this is to coax length, because the coax is in the middle of your resonant tank circuit between the tuner and your antenna. And yes, the coax is the primary recirculating loss in both directions of the output, forward and reverse power going through your system, recirculating here. So let's review, what does all this mean? Why do I care? And how should I think about this? Well, output power versus the S unit signal strength. Remember that every 3 dB cuts your output power in half. And 1 S unit is 6 dB, which means that your output power is 1/4 of your input power. But what happens if your contact has a signal of 1 S unit over the noise? You might lose them. What if you're operating 5 watts QRP or even 20 watts QRP plus? Okay, you could lose them easily then. What if the noise floor starts to rise? You'll lose them. So you're running really marginal is what I'm saying. If you're running marginally, and he's not just booming in, but right there on the edge, it can make a huge difference. Dropping half to 3/4 of your power could easily lose that contact. You might hear them, but they won't hear you. So what can you do about this? So let's say you've got a non-resonant antenna, which can be a great antenna if you know how to handle it. So you set your VNA frequency range, you maximize your measurement points, calibrate your VNA at the antenna end of the actual feed line, take a scan of the impedances over that range, save it to an S1P file, which is your impedance scan file, import it into your computer, drag and drop it into the file window of SimSmith, analyze the impedances, SWRs, powers, and bandwidths, and you can test it by adding devices like tuners and transmission line transformers and reactances like inductive and capacitive reactances. You take that, you list the impedances at each band of the desired operation, determine if you've got any natural match bands, determine which bands needs a tuner and are they within limits, determine the minimum transmission line transformer ratio that gets a tuner in range for more bands, update the antenna system, retest, reanalyze, rinse and repeat. So a few myths I want to kind of wrap up with and wind down is resonant antennas are measurably better than non-resonant. Not true. Non-resonant antennas that are well matched can easily be as good as a resonant antennas, and sometimes even better, because they very often can be done on multi-bands. A tuner at the rig end will tune the whole antenna system. Well, it depends on what you mean by tune. I wouldn't call it tune, I would say accommodate is more likely. A tuner accommodates it and keeps your, yes, it keeps your rig happy, but it helps the movement of your power out to the air on the antenna end. Reflected power at a mismatch will eventually be radiated. Not really. A lot of the power in a mismatched system gets absorbed by the coax, by that recirculating power up and down the coax each time, each iteration. And some of it will squirt out each time, and some of it will get reflected and recycled, if you will. So reflective power from a mismatch won't damage your rig? Well, unless you have a modern rig. If the older rigs did not have what's called a foldback circuit that pulls back on their RF power when it sees a high SWR to protect its final amplifier components. And you could blow out a final amplifier. People have done it many times. Tuners are inherently lossy or can absorb reflected power. In a modern tuner, it's not true. The series resistance of inductors and capacitors are quite good, so the loss, the ohmic loss, is very, very low. And so tuners are probably 98, 99% efficient, so don't worry about them. Tuners can compensate for any antenna mismatch anywhere, and I think it's the anywhere part that gets really people confused. Anywhere being anywhere along the system or any frequency. And that's not really true. It can help, and if you know what you're doing and paid attention here to this presentation, you would know how to handle it to get a good match in more places along the antenna system and in more bands. And a resonant antenna that's properly loaded means it radiates. Well, a dummy load is resonant and has a 50 ohm load, but it doesn't radiate very well. So you need a wire. You need some electrons up and down the wire, up in the air to radiate that electromagnetic radiation as well, and have some radiation resistance. So it all depends on several factors. So some takeaways. Resonant antennas have in-band SWR dips, while non-resonant antennas may not. They might get lucky in a few bands, but overall on a multi-band antenna, they're probably not going to all match up. Resonant dipoles are typically half wavelength on the lowest band, while non-resonance really can be anything, any length. You can use a pure transmission line transformer when the antenna is resonant on that band. That's what you see with an end-fed half wave. And if you do some, if you're very careful with the end-fed resonant half wave and give the right unknown with the right capacitance loading on that band, you can get pretty good matching on the main bands, not the work bands, but 40, 20, 15, and 10. A transmission line transformer can sometimes get the impedance into shooting range for your tuner. It could help a lot and make the difference between your tuner being able to tune in the work bands or not, for example. Using a remote tuner at the feed point for non-matched antennas is always preferable on a non-matched antenna. As I said earlier, anything less than 10 feet of coax between the antenna and tuner and the antenna is negligible. And feed line losses where the coax impedance is not characteristic 50 ohm impedance can hide impedance mismatches from the antenna. If your antenna is mismatched, that mismatch will actually propagate back down the coax and present it to your rig. And so it can hide and not really tell you very much about what's going on at your antenna. A few more takeaways. Calibrate your VNA at the antenna end of your feed line, and that accounts for the impedance differences I just talked about. Check that the tuner can handle high impedance mismatch bands. Okay, what can it handle, what can't it? Use a common mode choke at the feed point for all unbalanced antennas. Ladder line can be okay for long runs to non-resonant antennas at high power. That's where it still is a good tool to use. Realizing ladder line is high impedance of typically 400 to 600 ohms, but it's great if you've got an antenna that's 400 to 600 ohms. Remember, always keep your feed lines away from the grounded surfaces and keep your feed lines perpendicular to radiating elements. That's always a good thing to do. May your antennas always resonate and your radiations always propagate. So with that, I'll leave you with a couple of QR codes. This one's to this presentation in PDF form that you can download to review all this information. And this is a QR code to the TennaTalk series on my Antenna Whisperer YouTube channel. So if you like this video, please click the like button and hit the bell icon and subscribe to be notified of future videos. And I hope you guys got a lot out of this. And I would love to hear your feedback and your comments, and like to hear some ideas of what you'd like to see in the future. So with that, I'll say 7-3 from the Antenna Whisperer, Rudy, K7RAW, and have a great day. Bye-bye.